Thank you both organizers for inviting me. It's a pleasure to talk in this wonderful little workshop. And thanks, Martin, for being patient with me when I was slow at answering emails. So I need to move the Zoom window a bit away. There you go. So this is joint work I did with Christina Goldschmidt when I was a postdoc in Oxford. There's a paper on arXiv, but we're currently revising it. So if you want the paper, you're better off just asking me about it. So I'm going to talk about scaling limits. So we're quite familiar with scaling limits in probability theory. The general idea is that we take something which usually grows with the parameter n, and somehow when we divide it by the correct power of n, some interesting limit appears. So if we take a random walk and divide by root 10, if it's centered, then we get Brownian motion at the end. That's probably one of the most important examples. But nowadays, there's a lot of research around some rather interesting or exotic things. So especially in the world of graphs. So I'd like to mention, for example, David Aldous in the early 90s worked on scaling limits of random trees. And now we even have things like maps, which are very embellished graphs. And what we're gonna look at today, which is scaling limit of a directed graph. So this is a little bit of an unusual object since directed graphs. So the thing of scaling limits is that usually we have in the limits a discrete metric space. And directed graphs don't naturally become metric spaces as well because there's this whole thing, there's an arrow on each edge, and in the scaling limit, the arrows might disappear. Well, turns out Christina and I found that in this case, we do have something interesting. And this is what I'm going to present. So I just drew an example of what could be a directed graph. So we have a bunch of vertices and edges between them, and the edges all have arrows. Sometimes we can have two edges going from one in both directions between two vertices. And I always draw my vertices as little circles like that. This will pop up later. I'm seeing that things are being said in chat, I think, but I can't see it. If it's important, Matt, you can interrupt me.
Yeah, nothing about you.
Okay,
Yeah.
okay, very good, very good. So before we talk about scaling limits, I need my app to work again because it's not scrolling. I use the mouse. Sorry about that. So I'm going to define my proper model. So as I wrote here, we're going to call it GNP, and with an arrow on top of the G to say that it's a directed graph. And it's a random graph with a vertex set and an edge set. The vertices, as you kind of saw above, are just the first n integers. So above I went up to 17, I think. And the edges are a rather standard thing. We're going to do basically an edge percolation on the complete graph. So I have n times n minus 1 possible directed edges. I'm going to keep each one of those independently with probability p. So the probability of ending up with this specific graph would be p to the power of number of arrows I've drawn times 1 minus p to the power of number of arrows I didn't draw. Okay, and kind of like the Erdős-Renyi graph, I'm sure everyone is interested in, we're interested in the connectivity properties of this thing. And directed graphs have different connectivity properties than regular non-directed graphs because you can really define them in multiple ways. And here we're interested in what I call strong connectivity. We're going to look at the strongly connected components. And I'm going to give you a small definition. Two vertices x and y are in the same strongly connected component. I'll call those SCC. That's fairly standard. If I can go from one to the other in both directions. So to be sure that we're on the same page, I'm going to go back a bit and talk about the strong connected components we have in here. So for example, I can go from 1 to 2 just by using 5 as a midpoint. And I can go from 2 to 1 by using 17 as a midpoint. So 1 and 2 are in the same strongly connected component. In fact, we realize that we have a cycle, 1, 5, 2, 17, 1. So all of these four individuals vertices are in the same strongly connected component. However, I can't ever leave this block because I got two arrows pointing outside, but they're pointing from outside into the block. So I can't exit this set of four vertices, so it is an SCC. Similarly, we got 7, 11. They make a mini cycle. I can go from one to the other. So they're in the same component, and I can leave this component. Well, I can leave 7, 11, but I can't go back to them. So again, they form a strongly connected component. Let's do the list. 15 is by itself because I can't leave it. 10 is also by itself. I can leave it, but I can't ever come back. We got a big component with 3, 8, 9, 16, 14, and 6. That's mostly because you can see we can kind of go up from 3 all the way to 14 and using 16. And then from 14, we can loop back into 3. And the final 12, 4, and 13, they're all by themselves. We can never go back to them in any way. So that's strongly connected components. And it turns out there is a phase transition for these things, which is very close to the phase transition of the Erdős-Renyi graph, which probably most of you have heard of. So I'm going to take P, so my probability parameter, to be a constant over n. And depending on whether this constant C is above or below 1, we end up with what you could call a supercritical or subcritical regime. So if C is bigger than 1, there is what we call a giant strongly connected component. So giant means technically, well, in practice, that it has proportional to n number of vertices in it. And all the other strongly connected components are much smaller. So supercritical, there's a giant, and then everyone else is small. If C is smaller than 1, then we're in a subcritical phase, and all the strongly connected components are very small. I think in this context, it turns out that small means really bounded, so their sizes are like tight random variables. So this is something which was reasonably well known, and in fact, something slightly better is known, and this is what we're really interested in now. So this is fairly recent, 2009, by Wuchak and Zayerstad. And we place ourselves in the critical phase. So P is 1 over n, so between the sub and supercritical. And we allow ourselves a bit of wiggle room. The wiggle room is lambda n divided by n to the power 4/3, but the lambda n has to be small enough, so smaller than n to the power 1/3, to not push us out of criticality. And when we do that, we're going to look at what happens when lambda does tend to plus or minus infinity, just not too fast. And it turns out that we enter some phases which we could call quasi-supercritical, quasi-subcritical. So if lambda enters to plus infinity, the largest strongly connected component isn't quite linear in size, but has size n to the 1/3 times lambda n squared. It's still quite large. Meanwhile, the second largest is much smaller because we're going to get a big O of n to the power 1/3 divided by lambda n. So there's a difference of lambda n cubed if you divide one by the other. Meanwhile, in the almost subcritical phase, then the largest strongly connected component is rather small. It's the same thing as I had above, but now we need to take the absolute value of lambda n to be sure that this, that we get a positive number inside this big M. So this theorem gives us already some pretty good information of what happens. But of course, when you look at this, you're thinking, well, we're missing a big thing, which is what happens between minus and plus infinity. So this is the question we asked ourselves. What happened? So if lambda n stays bounded, or really if it converges, that's more or less the same thing up to extraction. And this is what Christina Goldschmidt and myself have worked on. So before I tell you what we ended up finding, I need to talk about what happens in the case of the Erdős-Renyi graph. So we're going to forget about directed edges for a little bit. See more chat going on, but I guess that was the abstract and things like that. I'll ignore this. So the Erdős-Renyi graph.
Yeah, I'll interrupt you if anything in the chat refers to the talk.
That is great. Thank you very much. So the Erdős-Renyi graph, I'll just say it out loud just in case not everyone knows, is the same graph, but we remove all arrows in the definition. So now we have n vertices, and n times n minus 1 over 2 possible edges, and we take each of those independently with probability P. And I take this P, as I said, we want the lambda n to converge. So I'm going to take a specific P. I need to have the zoom controls not hide my pen. I'm sorry about this. So I take P like this. So this lambda n I had before converges. So I should mention that lambda here is any real number. I never really am going to talk about this lambda. It appears in defining some of the things we'll see in the limits, but it doesn't actually play a crucial role in understanding what happens. Well, this is what we call the critical window, which is something worth knowing. So critical window is somehow how we go from subcriticality to supercriticality. And that was the theorem, of course, of Wuczak and Zajestein. So for the Erdős-Rényi graph in the critical window, we have some wonderful theorems given by some mathematicians who worked before me, and which will give us some very useful information for later on. First one is by David Aldous, so 1997. And it tells us what happens to the sizes of the connected components of my random graph. I call those Z1n, Z2n, Z3n, order them in decreasing order because that's going to be more convenient. And then it turns out there is a very good limit. So Zi divided by n to the power 2/3 converges in distribution to a thing called sigma I. So I forgot to put the n here if we want it to be very specific. So the sizes of each connected component are of order n to the power 2/3. And in fact, so this is a convergence in distribution. It's slightly better than that. It's in a convergence of distribution of sequences. So my sequence Zin, Z1n, Z2n, Z3n converges when rescaled by n to the power 2/3 in the space of L2 sequences towards this limit sigma I. I'm not going to tell you what it is, but it's a random positive number of which we more or less know the distribution. Next, second theorem, which we're interested in, more recent one, 2012, by Luigi Addario-Berri, Nicolas Broutin, and Christina Goldschmidt. So they tell us what actually happens to those connected components. So I'm going to call them CIN. And of course, they're going to be ordered such that the size of CIN was the ZIN, which I had slightly earlier. Then it turns out that I need to rescale CIN by n to the power 1/3, and then it converges in distribution to a thing I call curly CI. Now you may ask yourself, what does this mean? So my CIN is a connected component of a graph, so it's a graph itself. What does it mean to have a graph divided by n to the power 1/3 converge to a thing which is right now completely undefined? So the way we do this is we consider CIN to be a metric space. And we make it a metric space by saying that each edge is actually a line segment with length 1. Now we can rescale that metric space by saying we divide all distances by n to the power 1/3. And then as a metric space, this converges towards the metric space CI. And to make metric spaces converge, we use what we call the Gromov-Hausdorff topology or metric. So this is, as you inferred from what I said, it's a metric which is here to make metric spaces converge to other metric spaces. What really happens is that, so two metric spaces, X and Y, are very close in the Gromov-Hausdorff sense if you can more or less superimpose them one on top of the other and have very few mistakes. I'm going to stay hand wavy like that, but it's actually more than good enough for our purposes. And again, it's actually a convergence of sequences. So the whole family converges in distribution to the whole family of CI. So if you're a bit spooked out by this Gromov-Hausdorff convergence, the main thing we actually need to take away from that is that the distances, the typical distances in my connected component are of order n to the power 1/3. So if you want, I could take a random point in, two random points in CIN, then their distance should be about of order n to the power 1/3. That's more or less enough information for us here. But I will add one very nice and fairly understandable thing as an extra. So both CIN, a connected component, and its limit can actually be seen as binary trees with a few additional edges. What do I mean by this? Well, they look like something like that. So let me draw you a binary tree. I guess this is a binary tree. And there's a few, that's a bit too simple of one. Okay, let's do this. There's a few additional edges, maybe one here, and maybe one here, and maybe one here. And this is what my thing looks like. So this, this can be seen as a metric space if you just say that each little bit here, each little bit, each branch has a certain length. This defines a metric space. So in practice, the limiting ones are continuum random trees because we've taken limits, so they're actually very, very big, very dense, and so on. And if you've heard of the Brownian random tree, this is what we're talking about, really. But this doesn't matter too much here. A few additional edges. So in the discrete case, in the case of the connected component, it just means there's a way of selecting some vertices, and we add an edge between them. In the continuum case, we're saying that we identify the 2 points at the edge of on the edges of this edge, and we identify them. So in a way, you can say this edge has length 0. Okay, we'll come back to this later. Now, so that was a recap. That was information about the Erdős training graph. And now I'm going to finally talk about my own results with Christina about the directed graphs. So I'm going to start with an informal version, which is actually very visual, and we'll let you see what happens. And this is kind of a theorem, really. And it contains the heart of our result. So I'm back to my GNP. I still have P is 1/n plus lambda divided by n to the power 4/3 plus a little correction. That is not going to change. And within the strongly connected components, I have 3 interesting things which happen. The first one is that with high probability, there are no vertices with degrees 4 or higher. So that's kind of a strong statement. So this means that all the vertices have degrees 3, 2, 1, or 0, right? I'll mention that degree here means the total degree in plus out. But in a strongly connected graph, you don't have vertices with degrees 0 or 1, because you always need at least one edge which goes out and one edge which goes in. So this means all our vertices have degree 3 or 2. And we have good estimates on what happens with those. So the number of vertices with degree 3 is about of order 1. So I don't mean it's close to 1. I mean it's of constant bounded order. And the number of vertices with degree 2 is of order n to the power 1/3. So much bigger in a sense. Now, what does all of this entail? I'll do a little drawing. So we have vertices with degree 3 and vertices with degree 2. I'll call the vertices with degree 3 somewhat big. They have, as we'll see, a more important role. So let's say these 4 vertices I've drawn are the ones with degree 3. They need to be connected by long lines with vertices of degree 2. So we're going to have something which looks like that. I'm going to draw all of those. And I'm going to say this goes in this direction. Since we're strongly connected, they do need to go in the same direction. Otherwise, I'll create a breaking point. And remember, we said that the number of vertices with degree 2 is of order n to the power 1/3. So let's say, I'm being a bit hand wavy, but let's say this is about a times n to the power 1/3. A is a positive number. So we can do that with all of those. So I'm going to do this a bit faster because otherwise this might take ages. And however, those chains don't have to be unique at all. And we might have something like this going on. So to So on this vertical path, we can go both ways, but maybe on that vertical path, we can only go down. So this is a strongly connected graph with a number of vertices of degree 3, which is 4, so of constant order, and then other numbers of vertices with degree 2, those are of order n to the power 1/3. And here comes the interesting thing. Those vertices with degree 2, they're not very useful. They don't contribute to the structure of what's happening. The only thing which matters really is the number of vertices in each of those little parts, well, long parts. And really, I could erase all of those. Bye-bye. They've served their purpose. And replace them by a single long edge, which has same length, well, +1, if we were counting the number of vertices. And we can do this for all of that. So here we have 2 long edges, and I'm going to keep erasing because I want a proper look at what we get at the end. And there we go. So here we get something like that, and here we get something like that. And each of those edges has a length which is of order n to the power 1/3. And this is when you get another idea. Well, we're looking at the scaling limit, and we're thinking, well, lengths are of order n to the power 1/3. How about we divide everything by n to the power 1/3? And so we end up with, take the limit in a sense, and we get something like that in the end, right? So what is this? This is a directed graph. We have vertices and they're connected by edges with arrows, but it's actually a multi-graph. Because here, for example, that edge exists twice. So it was actually 2 different edges before, but when we did this little interesting operation of removing the useless degree 2 vertices, we made those be kind of 2 instances of the same edge. And of course, each edge now has a length. A, B, C, D are just positive numbers, really. And so we ended up with a new interesting structure, and we need to develop a little bit of things around that. But you can see what's going to happen. The theorem, which is almost peaking out, is rescale by n to the power 1/3, and we get convergence to this kind of object. So how do I call this kind of object? I call those metric directed multigraphs, and I'm going to abbreviate them as MDM. So we need to be quite specific about how we define those. So an MDM is a finite multigraph where each edge has a direction and a length. And I should insist that each edge is really identifiable and different from other edges which may connect the same vertices. So this is what we had above. If we scroll back a bit, so we had 4 vertices and a few edges. Each edge has an arrow and a length. So that defines them. I'm interested also in the notion of isomorphism. So this is going to ignore the lengths. It's just a discrete thing. An isomorphism is not just a bijection between the vertices, as it would be in the case of regular graphs. It's a pair of bijections, one for the vertices and one for the edges. And those have to preserve the structure. So in the natural way. So if there's an edge from x to y, and if there's an edge from x to y, then there should be an edge from f of x to f of y, and that edge should be g of the edge between x and y. And if there's multiple, then there's also multiple. And let's have a little example. I'd be delighted if people could open their mics and try and guess how many isomorphisms do we have between this little MDM and that one. There's no trick question yet. So if anyone is brave, I'd be happy to hear your answers.
Zero.
0, yep. Yeah, this one is simple because they're not isomorphic. And because here the two edges have the same direction and over there they don't. So yeah, that was 0. How about the next one? So as you'll see, this is technically the same graph because it's just a line. Well, it's two segments, one stacked after the other. How many isomorphisms?
1.
1 indeed. Here comes the slightly harder one. How many between these two guys? So I've drawn the same graph, so we know there's at least 1. But is the answer 1?
I'd say 2.
Yeah, you'd say 2, and you're right. So the reason, so if you think a bit about what an isomorphism does, it will need to always send a vertex to another vertex with the same in and out degrees. So you need to send this vertex towards that one and that vertex toward this one. So you don't have a choice for the vertices. However, the two edges have functionally the same role. They just link the top vertex to the second. So the two isomorphisms, so one of them would match the edges like that, and the other would match the edges like that. Very good. And we're going to see why this is important immediately as I define the distance between two MDMs. So I take two metric directed multigraphs X and Y, and their distance will be defined this way. I look at the best isomorphism, which minimizes the sum for all edges of the length of the edge in X minus the length of its image in Y. If it sounds a little bit mysterious here, just look at this example and you'll understand everything. If I look at the distance between these two multigraphs, so they very close, so 2, it's like before, so there are 2 vertices and 2 edges going from the bottom to the top, and we have 1 plus epsilon, 2 plus epsilon prime, and 2 and 1. So there's one smart isomorphism and one which is not smart. What is smart is you match the 1 plus epsilon to the 1 and the 2 plus epsilon prime to the 2. And then you see that the distance between those is just epsilon plus epsilon prime, so quite close to 0. If we had used the other isomorphism, we'd have 2 plus epsilon prime, so nowhere as good. I hope that's okay with everyone. And I'll finish this introduction to these objects and this metric by a remark. This is a very strong and rigid metric. So by which I mean things that we would like to be close, maybe in other settings, don't end up being close at all. For example, I take my graph, one of the simplest multigraphs you could think of, one vertex, and it's a cycle. And I modify it by adding a second vertex and a very short edge from the new vertex to the original. So this has length epsilon. Epsilon is very small. Then they're not isomorphic, so we don't have a choice really. The distance between those is infinite. But if we were using those Gromov-Hausdorff metrics I mentioned before, then the distance would be epsilon. Because in the metric sense, we only just added a line segment with length epsilon. So what I'm saying here is that this metric, since it's very strong, you might expect it to be able to prove fewer results than other more flexible metrics. But it turns out that it's convenient for our purposes. So that's great because it means our theorems are going to be very strong as the metric is. And finally, I can state the actual theorem. So I take my strongly connected components of my multigraph, of my directed graph G and P, and I do what I did before. So remove all the kind of useless degree 2 vertices and instead replace them by long edges. And then we have the scaling limit. So I rescale things by n to the power 1/3. We kind of guessed that. And then we have a convergence and distribution of my Ci of n towards mysterious curly Ci, which are not the same as before. Now curly Ci turns out to be, well, so they all turn out to be MDMs. And here I've said, so the sequence of them is, it's a sequence of elements of G, and it has interesting properties, plenty, but I'll tell you 2 things here. So it turns out that finitely many terms are just 3 regular multigraphs. So remember, we said we ended up with things of degree 3 quite naturally. And all the terms which are not actually 3 regular multigraphs, they're just cycles. A cycle is just one vertex and an edge from itself to itself. And that's our main result. Now I'd like to give you a little bit of an idea of how we prove this. Oh, yeah, I should have mentioned, this is a convergence of sequences again, and we have a proper metric for sequences of MDMs, which is so if we compare sequence A and B, we just take the sum, infinite sum of the distances between AI and BI. Okay, I don't know how much time I have left, but I have the organizer's blessing to go slightly over time. So I want to talk a little bit about where this comes from.
Yeah, you've got
how we can
6 or
prove
7
this.
minutes on the clock. So
Sorry?
you've got about 7 minutes on the clock.
Okay,
And then
I'm being quite slow, so I'll try and speed up. I did talk about a few things. So the thing which makes this proof work is a notion of exploration. So exploration is a thing we often use in graphs to make them look as to explain the structure in terms of a spanning tree or a spanning forest, which is then decorated with various bits and pieces. Here I'm going to do what we call a depth first search, or a slight variant of that. I'm going to take a risk and unzoom a bit so we have a bit more space. And I'm going to explore my graph and draw a spanning forest. And I'll explain how this works as I'm doing it. We start with 1, that's our smallest vertex, and we reveal its 2 out neighbors. So I insist we look at the out neighbors. So they're 5 and 17, because there's arrows going from 1 to 5 and from 1 to 17. When we do that, we say we have explored 1. 1 is done. Thank you very much. Let's move on to the next person. The next person is the smallest available vertex I have. That's 5. 5 has an out neighbor. That's 2. And we're done with 5, because 5 has no other neighbors. And now we look at 2. 2 has another neighbor. That's 17. So I would want to do this, but I can't, because 17 is already on my picture. So instead, I'm going to mark this. I'm going to put it maybe like that in red and also dotted to explain that this edge is fundamentally very different than what we had before, because 17 was already on my drawing. Okay, so 2 is explored. Now let's explore 17. 17 has an out neighbor, which turns out to be 1. So again, I can't do this. So I'm not going to do it. Instead, I'm going to mark this edge like that. I mark it in green. So why is it in green and not in red? Because there's a little bit of a difference between those two. One turned up before 17 in the planar order of this tree I'm drawing. So the planar order is the depth first order, if you like, is when you explore around the tree like that. And while 17 is on the right of 2, if you like, so we put this in red. 1 is on the left of 17, and so we put this in green. And I'm going to do this for the whole thing. So 17 being explored, we need to explore the lowest available vertex. But now there's no one on the tree, so we're going to start a new tree at 3. So 3 has out neighbors 8, 10, and 15. So we're going to do this. So 3 is explored, thank you. 8 has also 3 out neighbors, 6, 9, and 16. So that's very good. Now we explore 6. 6 has 2 out neighbors, 12 and 3. So 12 is new, so that's good. But 3 is not new, and we go backwards to 3. So that explores 6, then 12. 12 has 1 out neighbor, that's 2. 2 has...
Sorry, may I ask a question?
Yeah.
Shouldn't it be red?
So yeah, I said left and right. Left and right is not good. 3 occurs before 6 when you do the depth first exploration. And that's why it's green.
Okay.
But 17 is after 2 if we do depth first exploration.
Right.
So that's one way of saying it. Another way of saying it actually is that, so 17 had already been revealed when we were at 2, but it hadn't been explored yet. And that's why we put red. On the other hand, 1 was already revealed and explored when we were looking at 17, so we put that green. So similarly, here we're at 12. 2 has already been explored, so we put this as green.
Sorry, can you explain why you're exploring 12 there? I was expecting you to explore 9.
You're correct. You're correct. I said lowest number. That's wrong. We explore the leftmost every time.
Ah, right. Thank you.
Yeah. Apologies. Thank you. And since we don't have time, I'm going to just keep doing those. So we got 13, we got 4. So we'll do 4 first. 4 goes back to 12. Then 13 goes back to 4. And 9 is done. And then it's to 16. 16 has just one backwards edge like this. Then 15, 10 goes to 15. So that's red. And that's it. And then we have 7 and 11, which are just this, like that. So sorry for a little mess. So we ended up drawing a forest because we got 3 trees. And this forest, in a way, the forest is blue and is decorated with extra edges, which are green and red. And we're going to classify those edges. I'm going to call the blue ones, I don't know, tree edges. The red ones will be called surplus edges. And these 2 categories have the interesting property that they both go forward for the depth first order on the tree, which I did a few times. So as you explore around, climb around the tree like a monkey, then you see that those always go from a previous edge to a newer one. However, the green ones, I'm going to call them back edges for the main reason that they go backward. And it turns out, since we have a nice, nice linear order on those trees, the interaction between the forward and backward parts are what creates cycles, and that's what creates strongly connected components. So if I go back to what we had before, for example, I can go from 1 to 5 to 2 to 17. So that's a forward path. And then I go back to 1, and that's what closes the cycle. I can go from 3 to 8 to 6, that's forward, and then go back to 3, that's backward. Also, I forgot 11 to 5, but that's mostly irrelevant. Edges which go between different trees are irrelevant. Okay, so we have classified our tree into 3 kinds of edges. And it turns out that, if we can understand the limit behavior of those edges and how they interact, then we should be able to get our limit behavior for the strongly connected components. And there's one very wonderful result, which is this proposition. If I look at the forward graph, if you want. So we take the blue and red edges and forget about the arrows. So we just say this is now a graph. It turns out it has the same distribution as the Erdős-Rényi GNP. That's great. This means we already know lots and lots of things about these edges and those trees, because we can use the results I mentioned earlier. For example, the number of vertices in each tree is about n to the power 2/3. That's connected components of Erdős-Rényi. Typical distances are of order n to the power 1/3. That's the scaling limit result we mentioned. And the surplus edges are very few in number. They're only about bigger of 1 in number. So I didn't really mention that, but that's those extra edges I mentioned earlier. There's not many of them at all. And in fact, there's so few of them that they end up not mattering at all for strongly connected components. So here's another proposition. The probability that any strongly connected component has a surplus edge tends to 0 as n tends to infinity. So after this proposition, we can forget about those red edges. They don't matter at all. I'll give you a quick proof, a very quick proof. So it turns out that a red edge always looks something like this. So we have an ancestor, and it goes from one descendant to, if you want, an older brother of your grandfather. So it always goes something like that. And so we want to know, what's the probability that this red path counts, as in what's the probability that it's inside a strongly connected component? Well, this means that we would want something to start from this vertex here and loop back somehow into the source of the red vertex. So this means you'll realize we need either a red edge to go out of here or a green edge to go out of here. And by here, this little thing I drew, that's the tree of descendants of that vertex. So it's smaller than probability that we have a green, green goes the other way, green or red edge happening. That's an or. We just need at least one of those happening. The most nice thing we could have, shouldn't have erased that, would be, something like that. That would create a loop immediately, but maybe it's a bit more complex. But it turns out that this tree I just drew is pretty small. It's only actually bigger of 1 in size. That's because you can link these things to Galton-Watson trees, and you can see that it's mostly off the spine, and anything which is off the spine and ends up being rather small. So this is going to be smaller than bigger of 1 times p, probability of seeing any edge, times like n to the power 2/3, which is the number, 2/3 like this, which is the number of candidates for a target of a green or red edge. So it's smaller than very fuzzy n to the power 2/3 divided by n, because p is 1/n, and so that tends to 0. So that's why red edges are really irrelevant. So good, we know a lot of what happens to the blue and red edges. Now we need to know a little bit more about what happens to the back edges, and then we'll be done. So back edges,
just about 2 minutes on the clock.
Yeah, we'll be fine. We'll be fine. So back edges, there may be a little bit of a surprising problem. So if I look at a single tree, so in that tree, let's say there's k vertices, then we have k times k minus 1 over 2 possible back edges, because each pair is ordered. And each back edge appears independently, as usual, with probability p. But we said before that k is of order this thing, n to the power 2/3. So the expected number of back edges, so it's going to be, 1/n times this thing. And so that's going to be a positive power of n, 1/3. So that should tend to infinity. So we're saying there's going to be an infinite number of back edges in a single tree. That sounds very weird, because we said we had a rather finite and rigid structure. That sounds wrong. Well, turns out this problem can be solved, because it turns out most of the back edges don't matter. And by don't matter, I mean they're not part of strongly connected components. Why is that? Well, let me draw a very basic example. Here's a back edge. This doesn't create a cycle, right? You don't have a strongly connected component from this. However, if I created a back edge like this, now this would create a cycle, right? My cycle would be that small bit, which is hard to draw, really. And so the thing to do is we need to distinguish which back edges matter and which don't. So what's interesting in this one is that it's ancestral. So it always links you from yourself to an ancestor. And this is the crucial thing. So here's how you find the back edges which matter. You explore your tree in the depth first order, and you're going to chuck away all the back edges until you reach the first ancestral one. And after that, you're still going to chuck away most of them, but you're going to keep any of those which is ancestral, because those create loops, or links into something that we've already selected. So, because we might create a link, as you'll see when I do a picture, this way. When you do it like that, turns out that this selection process converges to a Poisson point process of back edges on that limiting continuum tree. And this is perfect, and it lets us finish the thing. I'll just finish the talk with a few improvised drawings. So let's say we have a tree, binary tree, looks like that. And we have maybe a back edge like this and a back edge like that. On one side, maybe we have a back edge like this here. And I'll add a few more things. So what's nice would be, for example, one back edge here and one back edge here. Then what do we end up with? If we just look at the strongly connected components. So the bit on the left would end up looking like that. So we have, well, we have one cycle here, and then it branches out and cycles back like this. I'm going really fast, so I'm probably doing things wrong. I am, I'm sorry. So like this, and then we have U goes here and U goes like this. This is bad, but that's all right. This one will be just a cycle. And the one on the top, that's probably our favorite one. So we have, as we can see, there's a big cycle around it. And then it has a smaller cycle, if you like. Sorry. It's going to be the theta kernel. So really it ends up, if I am not wrong, looking something like that. And the thing is, those are all three regular graphs or cycles. And that's why we have that thing we mentioned at the beginning, that in the limit, we always had three regular graphs or cycles. I'm going to stop here. Thank you for listening. There you go. And I'm open to questions, of course.
Thank you very much.